Hello students, this is Mr. Deaver, and in this video we're going to talk about acids, bases, their properties, and how they dissociate. I'm sure many of you have heard of acids and bases before, and especially when I say the word acid, maybe something really scary comes to mind, like some chemical in a lab that can burn you or eat through your skin. But acids and bases are not just scary chemicals found in the lab. And they're also not just instruments played by Flea from the Red Hot Chili Peppers. Acids and bases are found in our bodies and in many places in the world. So let's look at a few examples. Turns out that vitamin C is actually ascorbic acid. So eat your fruits and vegetables, kids, and don't get scurvy. Carbonic acid is another example. When carbon dioxide, or CO2, is dissolved in water, it creates carbonic acid, and this process is what makes many soft drinks carbonated. And the same thing actually happens when humans burn fossil fuels and release CO2 in the atmosphere. That CO2 dissolves into the ocean and creates carbonic acid, which then causes ocean acidification. So go see the coral while you can before it's all gone. And finally, acetic acid is more commonly known as vinegar. As for the bases, many cleaning products, ammonia or NH3, bleach, soap, and other cleaning products are basic. Milk of magnesia, which contains magnesium hydroxide as one of its ingredients, is used as an antacid and can treat indigestion. So you probably know that your stomach contains stomach acid and is very acidic. So isn't it interesting that we need a base or an antacid to counteract our very acidic stomach? And finally, calcium hydroxide. Ooh, that's the wrong formula for calcium hydroxide, isn't it? Aha, can fix it now. Okay, calcium hydroxide is one of the ingredients in mortar, which is used to hold bricks together. Okay. Now, we're not going to focus on pH in this video, but just in case you see pH in any of the resources on acids and bases, pH is one of the ways that we measure how acidic or basic different substances are. A lower pH of below 7 indicates that something is acidic. A higher pH above 7 means something is basic, and a pH of exactly 7 means something is neutral. We're going to talk a lot more about pH next week. Okay, let's talk about some properties of acids and bases. Now, when you think back to the examples of acids that you saw on the last 2 pages, you probably noticed that some acids are found in foods. How do these acidic substances like lemons and tomatoes and vinegar taste? Well, they taste sour. And in addition, acids often react with metals to produce hydrogen gas. As for bases, while bases aren't something that we should eat, so don't eat Tide Pods. If you've ever accidentally gotten soap in your mouth, how did that soap taste? Well, it probably tasted, ooh, that should say bitter. Probably tasted bitter, and soap probably feels slippery. Okay, cool. So both acids and bases are often found in an aqueous environment, which means that they're dissolved in water. And when they're dissolved in water, both of them can be electrolytes, which means that they can conduct electricity. We've previously seen that many ionic substances can conduct electricity when dissolved in water, so that gives you a pretty big clue for what happens in aqueous solutions of acids and bases. Hint, hint, dissociation. All right, if you've ever studied acids and bases before, you've probably used these infamous pH strips. There are many different acid-base indicators, but all acids and bases will change color in the presence of an acid-base indicator, although the exact color will depend on the specific indicator. Finally, both acids and bases, not just acids, can react with skin or muscle to cause burns. Now, Clearly, not all acids and bases are dangerous enough to cause burns, since we use soap to wash our hands and we put vinegar in our food. So how dangerous an acid or base is depends largely on how strong that acid or base is. And we're going to talk about the strength of acids or bases in our next video. Okay, now maybe you're starting to get an intuition for what substances in the world are acids and bases. But if we give you a formula, how can you tell if something is an acid or a base? Well, most acids contain H. For example, HCl is hydrochloric acid, and this is sulfuric acid. Both of them contain an H. In fact, if we look back at the examples we gave you of acids, all of them contain H's. Aha. Okay, what about bases? Well, bases usually contain OH, or hydroxide. For example, sodium hydroxide, NaOH, is a very common strong base. One exception to this, though, is ammonia, or NH3, which is a base even though it does not contain OH. If we look back at our examples again, we see that many of them contain hydroxide or OH, except ammonia, again, is a base, although it does not contain hydroxide. Okay, now I've already hinted that many acids and bases don't just dissolve, but also dissociate in water. So what does dissociate mean? Remember that dissociation is when a molecule splits into smaller parts. For example, salt or sodium chloride dissociates in water when it splits into positive sodium ions and negative chloride ions. Sucrose or sugar dissolves in water, so we can see that the molecules separate from themselves and interact with the water. However, they do not dissociate. They do not split into smaller particles. Each sugar molecule stays as one whole intact sugar molecule. As for acids and bases, many acids and bases dissociate in water, or break apart in water, kind of like salt. Okay, so now we are going to look at some examples, and we're going to write the equations for how acids and bases, or how acids in this case, dissociate in water. Now, we have a bunch of acids here, and notice that they all contain at least one H. So let's look at this guy, HNO3. How will it dissociate? Well, it's going to split into a positive and negative ion. The positive ion will be H+. And when the H dissociates, it ionizes or becomes a positive H+ ion, which is why we mention ionization here. What's the negative part going to be? Well, the negative part is going to be NO3, or nitrate. Remember that nitrate, or NO3, is a polyatomic ion. And hopefully you remember this sheet from class. This is our list of common polyatomic ions. So it may be helpful to review this paper. Now, when ionic compounds, or acids, or bases dissociate, they split into positive ions and negative ions. But the polyatomic ions do not break apart into individual atoms. They will always stay together as one whole polyatomic ion. So if you see something like NO3, it's going to stay as NO3. It's not going to break apart into N's and then O's. Or if you look at PO4, for example, phosphate, it's going to stay together as PO4, phosphate. It's not going to break apart into separate P's and separate O's. So, when HNO3 dissociates, it is going to make NO3. But let's talk about that H, because free H+ ions do not exist in water. Turns out that those H pluses are actually going to react with water here to make H3O+, or the hydronium ion. Now, sometimes you may see H+ written by itself, and sometimes chemists, maybe Kevin too, if there's any Kevins out there, but chemists talk about H plus ions. But when they talk about H plus ions, they're really talking about hydronium ions. Okay, if we ever say H plus, we really mean H3O plus. All right, and given that acids are going to make H plus ions when they dissociate, whenever you see H3O plus or hydronium, think acid. Okay, so finally, we can reveal the rest of our answer here. We're going to have NO3 minus, and then the H plus is going to react with water to make hydronium, or H3O plus. Now, notice that we have to write the charges on our products here in this equation. How do we know what those charges are? Well, H3O plus, or hydronium, is always going to have a +1 charge. For nitrate, for NO3, there's two ways to think about it. First, you could look at your list of common polyatomic ions and see that, aha, nitrate has a -1 charge. Okay, or you could think about the fact that these charges have to balance out, right? Because our reactants have a net neutral charge, the products also have to have a net neutral charge. So if hydronium has a +1 charge, then the other product, nitrate in this case, must have a -1 charge. Okay, let's look at our second example here, H2SO3. Okay, notice that there are two H's in this acid. However, initially, just one of those H's is going to dissociate and ionize. So whenever you see multiple H's, just remove, so to speak, one of those H's, okay? So our negative part is going to be just this minus one of the H's, okay? HSO3 minus 1. Okay, and of course, the H is not going to be a free H, right? That H that dissociates is going to react with water to make our old friend hydronium H3O plus. Okay, now how do we know this charge? Well, we don't actually see this polyatomic ion. Oh, no, we do see it here. Okay, it's on our sheet. Okay, so this is a polyatomic ion on our sheet, and we can see that, again, it has a -1 charge. So that's one way we can know about this -1 charge. But even if it weren't on our sheet, we know it has to have a -1 charge because the charges here have to balance out. Hydronium has a +1 charge. The other thing has to have a -1 charge. So really, in all your answers here, you're going to have H3O plus, hydronium, and then you're going to have your acid with one of the H's removed and a -1 charge. So pretty easy, right? Now, as a side note, it is possible for HSO3 minus 1 to go through another round of dissociation and therefore create another hydronium ion and become SO3 2 minus. Okay, this is what we call a diprotic acid because it contains two ionizable hydrogens. Most of these acids are monoprotic because they contain only one H, although this guy is triprotic. Now, even though some of these acids can technically dissociate more than once, in all of our answers, we're going to show just one round of dissociation and ionize one H, even if there's more than one H in the acid. Okay, so do the rest of these problems on your own, just like these, and you can check your answers online. But we have to do one more thing in this video. We have to talk about the dissociation equation for bases. Now notice that we do not show water in our reactants here, so all we have to do is write the positive and negative parts of each base with the correct charge and also the correct coefficient. So let's look at magnesium hydroxide, MgOH2. What's the positive ion going to be? Magnesium. Well, what's the charge of a magnesium ion? Well, hopefully you remember about ion formation. Magnesium is right here in column 2A, And all elements in column 2A have 2 valence electrons. So the easiest way for them to have a full outermost energy level is to lose those 2 valence electrons. And since electrons have a negative charge, losing 2 electrons makes a +2 charge. Remember that electrons are like a bad boyfriend or girlfriend. If you gain a bad boyfriend or girlfriend, your life gets more negative. If you lose a bad boyfriend or girlfriend, your life gets more positive. So the metals on the left side of the periodic table here, they are going to lose electrons and become positive. Okay, the nonmetals on the right side of the periodic table, they are going to gain electrons and form negative ions. Now, it's okay if you don't remember all these details, but you at least have to know this. You have to know that all of the elements in this column are going to form +1 ions. These are going to form +2 ions. These are going to form +3 ions, -3, -2, -1, okay? So magnesium has a +2 charge, so we're going to write magnesium +2. What about OH, or hydroxide? Well, if we look back at our sheet of common polyatomic ions, we see hydroxide here. It has a -1 charge. There's also a 2 here, though. What does that 2 mean? That 2 means that there's 2 hydroxide ions in the compound of magnesium hydroxide. So when this compound dissociates, how many OH particles will there be? 2. Therefore, we have to write a 2, a coefficient of 2, in front to show that there will be 2 separate hydroxides, each with a -1 charge. Now, notice as well, this means that our charges balance out. There's 1 magnesium with a +2 charge, and there's 2 hydroxides, each with a -2 charge. That means the net charge of our products is 0, just like the net charge of our reactant, magnesium hydroxide, is 0. Okay, one more example, aluminum hydroxide. This is going to dissociate into aluminum and hydroxide, but of course, the tricky part is to get our charges and our coefficients correct. So what's the charge of aluminum? Aluminum is right here in group 3A. Okay, everybody in that group has a +3 charge, so we have aluminum +3. Okay, hydroxide always has a -1 charge, and since there's 3 OHs in the compound, we will get 3 OHs when the compound associates. So we have to write a coefficient of 3 in front because there will be 3 separate hydroxides, each with a -1 charge, after aluminum hydroxide dissociates. Okay, it is time for you to do the rest of these problems on your own and then check your answers. Good luck.